Distinguished guests, I would like to welcome each and every one of you to SAHA Academy Talks presentation. Composite Aerospace Structures Advanced Manufacturing through Automated Fiber Placing is the name of the presentation that's going to be made by Dr. Onur Coşkun.
Welcome to the SAHA Academy Talks presentation. Now to present the project Advanced Manufacturing of Composite Aerospace Structures via Automated Fiber Placement. Please join me in welcoming Dr. Onur Coşkun, Chief Engineer of TR Motor, to the stage with a warm round of applause. The stage is yours, Dr. Onur.
Merhabalar, ben Onur Coşkun.
Hi everyone, my name is Onur Coşkun. I'm the Chief Engineer in TR Motor, and I have studies about the composite structures. I would like to thank to SAHA MBA, and one of the projects that we implemented is about the fiber placement, and I would like to thank them for their kind invitation. Today I'm going to talk about something which is not implemented in Turkey right now, but many international companies have started to adopt this method, automated fiber placement. There is a robotic arm, and it is placing the fibers on complex geometries. Why this topic matters now? This is relevant to aerospace, and the fields are related to aerospace. The weight is very important in aerospace industries. We need to decrease the weight, and in order to do so, we need to have automated systems. As high amount of structures, high number of structures are required in the sector, a qualification is required for the materials produced, and that qualification should be made through a system, not a person. And we need to be a pioneer, we need to increase the sovereignty. And for countries building aerospace supply chains, AFP can compress the leap from component production to certified structures. My presentation will last for 30 minutes. I will give you some brief information about the definitions, what is composite material, the hand layup, autoclave, etc. Then I will start talking about AFP, then market reality, and then I will be talking about the financial screening and adoption in Turkey. I will be showing you the prices as well. This is a composite structure, and a composite is an architecture, not a single material. When we say composite structure, we mean that it's a structure designed within the body of a helicopter, for example. Carbon fiber carries most tensile and stiffness loads. Orientation is the design variable. The fiber that you see on the screen, there is matrix inside, and we are looking at the defaults as well. You need to know need to know about the material. You're not here replacing it. You're creating a structure, you're creating an architecture. When you know about it, you know half of the requirements. And here we have a resin inside, thermoset or thermoplastic. Thermoset is used on the airplane. We have been using them for a long time. They are cure driven. It's like a resin, and once it's hard, there's no going back. When there's an issue, there's no way to repair it. But thermoplastic, it is weldable, repairable, recyclable, and once you heat it, you can change the shape. When there is a problem, then you can repair it. And as I said earlier, you can weld the structures to each other. Thermoplastic is a high-tech material. Thermoplastic is more advanced than thermoset. Okay, conventional composite manufacturing routes before AFP. What do we have? If we don't use AFP, what should we use? You can see here the methods input format, hand width layup. An operator comes there and puts the fiber, then two different infusion methods within the oven, they can work on it. This is low tooling cost. This has low tooling cost. But it is totally up to the skill level of the personnel. After that, prepec and autoclave, you can use that structure. This is a little bit more expensive. There should not be any air left, or there should not be any defect. You use autoclave with pressure and high trap temperature. We have vacuum infusion. This is for the aerospace parts, wing for example. You dry stack and then vacuum resin flow. It is for the large structures, lower pressure and more process sensitivity. And this is for the asymmetrical structures. And you use a hand RTM and HBRTM. This is a closed mold injection, and it's a good method, but of course each has some limitations. Till filament winding, there are some limitations because of the operator or the process. Pultrusion, this is already being used in pipes. It shouldn't necessarily have to be asymmetrical always. This can be used in continuous profiles. And ATL is the automated tape laying. On a normal surface, let's say that you use a big head, you can place the fiber to the surface. As your complexity increases on the surface, AFP comes, because at this point you need to use a robotic hand. I will give you the details in a minute. When I say conventional thermoset route, we will use the thermoset. And what do we do conventionally? We take the fibers and we cut the textile and put them on a structure. Then on the right hand side we use vacuum bag, and curing happens, and under the temperature of the autoclave you cure it. This is all handmade and manually operated. From the beginning till the end, you have many waste materials because you cut it, and all the textile materials, they're in a specific size, and the remnants are the wastes. Let me talk about the thermoplastic route. You can see here the body of an Airbus plane. They do welding on thermoplastic. You can't use thermoplastic In a dry format, there has to be a sheet structure because thermoplastics are hard in room temperature. You need to use it in UD tape or organosheet format, and these are suprastructures, and these are demonstrated projects. And here, in manual layup, we started skill intensive. You can see here placement and manual layup, then kitting, laser projection, and then ATL with the white tape or flatter parts. AFP has narrow toe and complex geometry, very small tapes, and you can use the robotic hands. You can design it from scratch. And last but not least, if closed-looped AFP with the inspection and adaptive control, this is going to be in a digital twin structure. You will get the scan data, you will compare it, and you will update the models. This is a closed-loop factory, and this is the closed-loop AFP method. You're not only bettering your manufacturing process, but also you are making the whole manufacturing structure a closed loop AFP. This is the structure that I am talking about. On the right hand side you see the cross section, and here you can see the shape of it while placing. There's fiber feeding, and you see here some bundles, and there are rollers. We take the fibers inside. There might be either one fiber or hundreds of fiber, 30 fibers. It depends on the size of the machine. Small fibers. It can cut and it can restart the machine. A complex geometry here. On top of it, not only placing but also complex placing methods can be used. Steel fiber is, another topic. How do we place the fiber at a certain angle, 40, 45, 20, 30 degree? In my doctorate thesis, I worked on that, and this structure not 45 or 55 degree. It depends on the load that you have, and as a result of the optimizations, the fiber path is going to be designed according to the size of your load, because there are cutters on top of it, and the cutters are cutting the material and the fibers, and the robotic arm can turn and they can prepare a fiber in the shape of C. You're using flap, let's say, for the air surfaces in order to direct any structure. In the warcrafts, if you can do flex coupling in a composite that you're using, a physically defined fiber, let's say axonal shift behavior or other behaviors, if you can couple them, you're not going to need an air surface with the angle changes. This is very technical, I know, but when you pull a structure, you expect it to stretch, right? But when we say flex cup, when you pull it, it bends. That is the feature of composites. When you pull it, the structure starts to bend, and it's like the air surface, it bends, and under that aerodynamic load, it starts to bend. And what AFP brings to us, it's a good technology, and it gives us advanced level designing ability. And this is the AFP method. You can look at all these pictures. You can see here the placements. The surface is quite complex. it would be very expensive to do it manually. You can't control the right whether the angles of the placement are right or not. There should be, it is certain that there would be gaps left. I mean the cracks. Or when you put the structures on top of each other, if it is aerodynamic surface, there is going to be a problem. So the resin infusion is less than the feature of the structure changes. This is not only a material, this is an architecture. There is resin inside, carbon fiber inside, and it has different percentage, 50 to 50, 30 to 60, let's say, and it behaves differently. So you use prepped. You put it with the angles that you wish. If you have a spar or panel, okay, you can put it with thermoset. You define it to your computer, then that robotic hand goes and produces that. You don't see surprises. This is how we approach thermosets. Thermoplastics is the same. We can do the same procedure. We can use the same procedure. This is a demonstrator project by Airbus. They go there and they weld it from the connecting parts. It might be ultrasonic or an external energy. They heat the points and then they can weld very fast. That is one of the features of thermoplastics. They can be cured very fast. Apart from the aircrafts, in most of the UAVs, this structure can be used in AFP. When you look at the structures in Boeing, they don't go manually. They use automated fiber placement, and good institutes mostly use this method. There are people in the world with serious experience in this topic. And again, in the space launch, you saw these structures and hydrogen tanks. Hydrogen storage is another topic, and you need to do the calculations in order to be able to store the hydrogen, and such structures can be produced with automated fiber placing. In Sabancı University, they do have such system. You can go there and use it. And in TAI, they do have some projects. And these are the companies that you can buy these robotic hands. It's not only about buying the robotic arms. You need to know how to use it. And these structures are going to have different capacities, the cutting capacity, the turning angle, software, etc. This is all digitalized. Therefore, if you're going to choose one of the structure, then you have to be careful about all these criteria. If we stop using the conventional approach, we have AFP machines. What do? We check our material yield. It's going to have narrow toe placement and optimized courses, and it can reduce scrap versus manual cutting, and it's going to leverage the labor because operator supervises machine and data rather than placing a reply by hand, and there will be certification processes in that regard. So it's going to be very comfortable in certification as well, because the programs, the softwares, all the digital components can be defined. You're going to have quality records because digital path, force, temperature, and inspection data support will be able to repeat it, and it will also give us design freedom in street fibers and in local reinforcement. It will enable lighter structures, and the rate will be high for qualified part families and stable process windows. The highest rate belongs to the body, and you need to have a proper design. Once you have the structure, the quality and the timing are going to be definite. If you buy 3 hands, for example, arms, then it's going to pay back very fast if your sales rates are high. Why should we move toward AFP in Turkey? When you look around in SAHA Expo, there are many UAV and defense, and the demand is high. It has to be composite because it's very flexible, and you don't need to work on the metal because it's very heavy, and there's no human inside, so it requires less certification. Therefore, on the right hand side, this is one of the real projects. If you have such a structure, it might be Aksungur Akıncılar or some other different examples from the world. If you have the cast without manual power, you can do it in a controlled fashion, and you can export it. You can cash it out very fast. If you're using thermoset, let's say, right now, and you would like to continue with thermoplastic, you can complete the transition period very fast because there is a defined process. You can change the materials. And the mentality here is that if you need to train your workforce. These are all high-tech works. You need to provide training to your technicians, to your workforce. You need to upgrade them. Rather than human beings placing the composite, you need to have a team with digital intelligence. So you need to have a team which can adopt technological changes and developments. And as for the supplier ecosystem, once you place it here, while doing so, you can also do image processing on top of it. You take the picture of the structure digitally. While I place it, let's say that I'm on the first layer. I do the first layer, then I have the visual of the first layer. And I know the points, the gap, the overlap, everything, and I can store. And on the second layer, then third layer, and I can also do the inspection and the placing, and I can interfere the manufacturing process. Therefore, whatever you do here in the subcontractors, the secondary, the sensors, tooling, inspection, software, and maintenance, slip tape, you're developing the subcontractors because the structure that you use have specific requirements. There are some companies working robotic. If you're going to export something, at the end of the day, it's going to be your need, and you're going to be looking for local producers. The sensor technologies, tooling, inspection technologies are going to develop slowly. Okay, if you would like to start it tomorrow, what are we gonna do? the mentality normally is to go and buy that robotic arm. But that's not the topic here. You need to select the part. You need to define the part. After defining it, it might be a complex or repetitive or composite intensive parts. Then you have to define your material route. Thermoset or thermoplastic, which material are you going to pick up? Once you pick up the material, let's say thermoset, what are you gonna do? You need to adopt digital design rules. The gaps, overrates, reduce, strike, reduce, you need to come up with a design according to the digital design rules. So we did design for manufacturing. Then what did we do? We defined the structure. Then we defined a pilot cell. And we picked up this cell according to our design. This is what we would like to produce. And in order to produce it, this is the size, this is the shape, etc. And you can find it all around the world. And after that, we are going to do the qualification. We produce something, then coupon, sub-element, element, full-scale articles. Then we turn it into a production system. If you start this program, what are the risks? Wrong first part is the biggest risk. You should start with part families that have high labor or scrap today and stable demand. Material supply mismatch. You need to qualify tape width, resin system, tag storage and slit quality early. It's going to be a part of the supply chain. Defect management. You need to build acceptance criteria for gaps, overlaps, wrinkles, porosity and waviness. You need to inform the designer well. We need to correct the defects. That's our design mentality. If we work with metal or aluminum, it doesn't matter. The life values, the temperature, operation temperature, we have some values coming from the production. Ultrasonic inspection, we define them. Then software under investment is another risk, You need to plan the path and also simulation and NC programming, because they're going to be your core process assets. You need to train your personnel as well. Inspection bottleneck, you need to integrate in-process inspection and NDI from pilot phase, not after SOP, because that is the main advantage of AFP. And qualification drag, you need to have a certification evidence plan. These numbers, that I give, I did the calculations and I took this data from public. In Aksungur class, let's say we would like to do Aksungur class AFP facility. In Turkey, we will see the humanless aircrafts, and I need to be focusing on the quality. I need to be decreasing the weight. Therefore, in total, AFP cell, tooling, cure, handling, autoclave, trim, NDI, metrology, digital thread and qualification softwares, facility integration, plus contingency. You see the numbers, the range for the 24 meters wingspan or 15 meters structure. In total, between 15 to $50 million. This is the range. One AFP cell plus core cure plus trim plus inspection software training tooling and integration. This is low rate for the low rate facility. And if you say two cells, production ready, TP ready option, different thermoplastic thermoset structures can be produced simultaneously, etc. Total cost is between 40 to 80 million dollars. The cost is quite high. You can say that hand layup, the labor cost is quite low. Why should we invest such big numbers? You need to, it depends on your income. If we can accelerate some stuff, what kind of an advantage is it going to bring us? When you sell, let's say, uh, 13 instead of 10 in a year, then of course it is going to be very advantageous financially. So this is public data. I'm not very knowledgeable about them. You can see here the references. You can see the numbers. On average, this is packaged, by the way, not only the aeroplane, the sensors, everything are included. Export package, $15 million Bayraktar. If Anka S, $30 million. If high-end package, this is American aeroplane, 150 million plus is the total cost. We have three cases, three scenarios. The first one is the conservative, when ISR only, limited support, and 10% of facility contribution. And first year first, second year two, third year three, fourth year four sales units year. This is the conservative scenario. And as for the base scenario, armed or maritime ISR package, 15% of facility contribution, 2, 4, 6, 6. And we have upside scenario, $35 million, like the Anka S structures, SATCOM, sensor support. 20% is going to come as, no, 20% is going to be the production cost, and 36888 UAV units per year. These are the sales numbers. Okay, this is the profit time analysis and payback. On the right hand side, you see here the capex, $35 million and $60 million capex. We have two factories, let's say. I need to make certain number of sales, but I'm looking at the cash flow. If it is $35 million investment, when I'm going to earn this amount, the profit margins are different. That's financial calculations. This is just for the screening purpose. This is the graphic. Base case, when you sell 10 products in total, 2.6 years, so you take the capex back, then your profit and loss calculations, etc., it depends on your facility. So the return on investment is huge. If you can sell 10, you're not going to sell it on your own. You can sell it to someone else because it's a robotic arm with the NC codes, with a cast, you can also sell to a third party as well. When we say upside, in total, let's say that 5 payback units, 1.3 years. Therefore, the money you spend at the beginning, if you consider it only as an investment, might seem very high, but if your production rates are high, then the money will come back very fast. Okay, these are the takeaways. AFP is not only a production technology, it's a strategic manufacturing capability. And when you would like to manufacture fast in a strategic manner, then it's going to give you that ability. An AFP is most powerful when the product is designed for automated layup, inspection, and traceability. These are three pillars of digitalization. These three pillars are all about big data, then digital twin, then AI. When you bring all this data together, you will notice that with the new AI mentality and with the image processing, when you can trace all of them, then AI defines the better methods that you can use. It's going to happen with the regression models. For Turkey ecosystem, the advantage is not only lighter parts, it's a faster climb into certified, exportable, and it is including certification. I can produce the body of an Airbus, for example. Once you are certified, your export rate is going to increase. So you become a company with great skills and abilities. So AFP investment, is going to come back with serial production and export programs. And when we make a projection in Turkey, we have serial production and export programs, not only in your company, but a couple of companies can come together and set up such a system, and you can have serial production and your costs might decrease. That's all I'd like to explain today. Thank you very much for your participation.
Bu değerli konuşması ve katkıları için Sayın Doktor Coşkun'a ve siz değerli
Thank you very much, Dr. Coşkun,